having me here and for organizing this fantastic thing. It's not that I'm only very close to this from the scientific part. The microphone? This way. I will try.
Now you're a star.
No. So the entire topic is very close to my heart. I have a sister who's an architect. My mother works in planning. And I've been around this ideas of interfacing between geometry, physics, materials, and aesthetics and art for quite a while now. I have tried to sidestep most of the equations, and I may have succeeded, but may have not. Geometric frustration naturally arises due to the mismatch between the non-Euclidean geometry, intrinsic geometry, of growing and forming bodies and the ambient Euclidean geometry. This is the central claim of this talk, to which most people will respond with a, huh? What's non-Euclidean intrinsic geometry? What's Euclidean geometry? How our growing and forming bodies are different? In what ways are they distinct from the other classes of bodies we know? Answering this and explaining this slide would essentially constitute the next 20 minutes.
What is ambient? I don't understand. Ambient geometry.
Thank you. Thank you. So the story starts here. This is a depiction of Euclid about 300 years BC. And what Euclid decided to do is to unify the entirety of geometry, basing it on but a few postulates. And he succeeds. And in a series of 13 books, he writes down his 5 postulates and bases the entirety of known geometry at the time, which was quite a big body of literature, on 5 things. And those are 5 relatively innocuous assumptions. If you give me 2 points in the plane, I can pass a straight line between those 2 points. If you give me a finite line segment, I can extend it indefinitely in both directions. If you give me a point and a distance, I can draw a circle with a distance as its radius. All right angles are the same. And then comes the 5th one. If you give me one straight line and 2 other lines cutting it perpendicularly, then when I extend them, they remain equidistant from each other. For a long while, this 5th postulate troubled Euclid, and he was trying relentlessly to prove that this assumption could be deduced from the prior 4. Unfortunately, he died unsuccessfully. Regardless of this, these 5 postulates constitute the entirety of geometry that haunted your high school years. Every single result you know in plane geometry, for example, emanate from those just 5 innocuous assumptions. For over 2,000 years, people have tried again and again to prove that Euclid's 5th postulate could be deduced from the prior 4. It became this sort of pitfall of mathematicians. Farkas Bolai in Hungary tried this for a while, and when he abandoned it, he focused most of his attention to training his young child prodigy, János Bolai. And then he heard that János was trying to solve Euclid's 5th postulate, and he pleaded, for God's sake, please give it up, fear no less than sensual passion, because it too may take up all your time and deprive you of your health, peace of mind, and happiness in life. Kind of like social media. János is now deterred, and at the age of 23, he solves it. But he doesn't prove that the 5th postulate comes from the prior 4. He actually discovers that you can relax it. You can completely relax the parallel postulate and get entirely other geometries that are slightly different. So in principle, on the left here side, we see Euclid's 5th postulate. We have 2 parallel lines emanating from one common line. There are 2 basic ways to contradict this. Either that you have no parallel lines or that you have infinite parallel lines going in between a line and point. In this geometry, where every two lines that emanate perpendicularly from a common straight line eventually meet, they draw closer and closer to each other, we call this a spherical or elliptic geometry. And it's noted by this quantity, which we call the Gaussian curvature. I'm not going to relate to it. But in these sort of geometries, the Gaussian curvature is positive. Lines that begin parallel eventually converge. And in the other type of geometry discovered, it's called hyperbolic geometry. We have negative Gaussian curvature, and essentially lines that start off mutually perpendicular to a common straight line diverge. These are actually more familiar than you think. Spherical geometry is the geometry of the sphere. If we can think of the equator here as a straight line, and then longitudes are also straight lines. But if you think of this as a big triangle, you realize that those lines emanate perpendicular to each other and then eventually meet at the pole. The opposing geometry is also quite intuitive. It's that of saddle, or imagine Pringle looking like surfaces. Triangles have less than 180 degrees as the sum of internal angles, and commonly perpendicular lines diverge from each other. The Euclidean geometry, though, pertains not only to straight lines and triangles. Every single result we know in geometry essentially can be traced back to those 5 postulates. In particular, in crystallography, one of these results says that if we have a periodic crystalline structure, and by this I mean a structure that if you map all the points by a translational mapping sideways, the structure comes back to itself. So if we have a spatially periodic structure, then it is limited by the types of rotational symmetries it could have. What kind of rotations map the system to itself? It could be either twofold, so it rotates 180 degrees, it comes back to itself. It can go back to itself after a third of a rotation, after a quarter of a rotation, or after 1/6. There's no other rotational symmetry allowed for a crystalline structure. That also comes from Euclid's 5th postulate. Now the thing is that if I try to tessellate space with hexagons, then we know I can. But what if I try to tessellate the space with heptagons? So Euclidean geometry says I can't, but the heptagons don't know it. So they might attempt to, but if they're perfectly rigid, then once I connect 2 of them, then the third one doesn't have enough of a head angle to go in. What if I make the game slightly different? What if I give them a bit of elasticity? So now everyone is going to make a compromise. Now I'm going to try to do something I can't. So this structure, by the way, would live very happy on hyperbolic geometry, on surfaces that look like saddles. Unfortunately, I'm making it live in the plane. So here's the game. On the left here, you have a bar that measures the elastic energy. Just 1 heptagon in the plane, everybody's happy. 3 heptagons, there's a slight reddish tinge. They squish a bit. You have to squint your eyes to see it. It's not very much. 8 heptagons, you see they're uncomfortable. 15, they're way more uncomfortable. Note that the scale bar is the same for everyone. It means that stresses are enormous, and they grow very rapidly as the structure grows in size. Moreover, I cannot think of this structure as being composed of subsets of this. Okay? This sort of compromise is highly cooperative. It knows how big my system is. It cares about the spatial extent. The type of compromise I did when I was this size cannot be copied verbatim to make twice the size. I have to do something different. And in that respect, predicting the shape it will give me becomes a non-trivial task. When I'm casting, though, when I just take a standard production process, I'm doing something else, okay? I'm taking every bit of material and I'm putting exactly where I want it to be. I'm controlling the configuration of things. And consequently, the object that I've just cast has complete compatibility with the ambient space, with the space in which it lives. It completely obeys the Euclidean geometry. And what do I mean by that? So when I curve something, so imagine this as the bottom part of that pot, then the uppermost layer has to be longer than the innermost layer because it's curved. There has to be more material on the outside to traverse the more length. But wait a minute, it doesn't have to just bend. It also has a spherical geometry. So we know that if I emanate two lines from the bottom, then the tangential geometry of this thing has to be that of a sphere. And all of these things are simultaneously obeyed because I cast it in our space and it went into its final position. Nature doesn't work that way. It doesn't put things in their final position. What you see here are tubulin heterodimers forming microtubules. This is an artist's rendition. What these microtubules forming proteins are doing are they assemble by locally finding the most preferred distance from each other and the relative orientation they would like to block. And these local tendencies give rise to shape, but they don't correspond one-to-one to shape. It's a different sort of process. The shape emerges from this prescription of local distances. And if you think of growing petals in a flower at just the edge of a daffodil, then the way it grows and the way it shapes itself is very different from the way we cast things. It doesn't obey all the laws of geometry. Essentially, it can choose a few of them. I think that the most striking example one could think of is that of a torn plastic sheet. If you just take a simple plastic sheet and you tear it, then its edge experiences plastic deformation. These plastic deformations elongate the edge. They don't bend it up and then down and then up and then down and leave all these cascades. The upper layer is not any longer than the lower layer in any specific region. What I've done is I solely increased the amount of length the edge had. And because of that differential elongation, because of the need to accommodate that, I have to buckle out of plane and make these ruffles. From a bending perspective, the top layer and the bottom layer are exactly the same, so locally it would like to be flat. So how can something be simultaneously locally flat and have the geometry that corresponds to something very hyperbolic, that has all geodesics diverging from each other? Well, it can't. It has to choose and make a compromise. And it turns out that what these materials choose to do is compromise on the bending. So what they do is they accommodate all the excess length, but they choose the shape that has the least amount of bending while doing so. And this is actually quite robust across a wide variety of systems. What you see here is a torn plastic sheet that incredibly resembles a big leaf. So this strategy is repeated again and again in many different systems. Of course, this dates back to all sorts of manufacturing techniques. When you crochet, you don't prescribe structural gradients across your monolayer of knits. What you do is only control the planar geometry of your structure. The shape emerges from the shape that bends the least, but accommodates the number of eyes you have at that specific layer. Eran Sharon and then Eric Klein, who's here, mastered this technique and were able to controllably dictate planar geometries that would result in specific shapes as their bending minimizing embeddings. This brings me to the other side of this, which is the inverse design. The inverse design is concerned with a slightly different question, and I'm going to address it in the context of a nematic elastomer. Nematic elastomers are types of materials that I'm not going to go into the nitty-gritty of their details, and there will be a few equations, but you can ignore them, that have some local orientation field templated on the material. And when you actuate the material, typically the ones I'll show are actuated by heating, but there are other systems actuated differently. They shrink along one direction and expand along the perpendicular direction, and they shrink and expand by the same factor everywhere. However, they always shrink along the direction of these local orientation fields, and they always expand along one direction and shrink along the perpendicular direction. So the actual director field, the actual texture, is going to determine the shape. The direct problem is concerned with asking, if I give you a texture and I activate it, what would it look like? What kind of geometry would it give rise to? And it turns out this could be solved. Of course, if all lines are straight, a square will become a rectangle. So these things have to curve and meander in space in order to do anything interesting. But what those interesting things are fairly well resolved by now. The inverse design is addressing the opposite question. It asks, I want to get that shape. What do I do? What kind of texture can I make that gives me that shape? That specific question is fraught with a main difficulty. The main difficulty is the following. I'm interested in understanding what is the texture in flat space, the one that I can fabricate in the lab, such that when I actuate it, it gives me the desired shape. However, the desired shape needs to map to the shape I made in the lab. And if I know that mapping, I already have the solution I'm looking for. So the most crucial ingredients that essentially tells me how do I relate the shape I want from what I can do in the lab is the main challenge that I'm trying to solve. So in between the solution and where I'm at, there's a big gap that does not communicate well. We eventually were able to solve this by understanding again that if we could think locally, we don't need to think of the mapping that gets me from where I'm at to where I want to be. I could look at where I want to be and ask locally, how does the director field around me bend? How does the opposite, the perpendicular director bend? How does it locally splay? How are the local properties in the distorted shape look like? And it turns out that those local properties could be all stitched together one to the other and solve the inverse problem. So again, the main point was to look at the local, understand how many local tendencies come together to give me shape, and then pull those back to the body as a whole. Consequently, we were able to show that you could get spherical, hyperbolic, mixed surfaces, a variety of geometries. But we were also able to discover that you could get the exact same geometry, in this case, spherical geometry, by completely different means. So there are many paths that all lead to the same eventual result. What's exciting about these results are that once you resolve a certain class of results, they immediately apply to a variety of different systems that all employ the same principles. So everything we said does not necessarily relate to pneumatic elastomers or a specific type of a physical material, but could be relevant to the bowel mold, which is actuated by pneumatic pressures, and other systems that employ mathematically similar principles. To summarize, when we typically think of assemblies, we think of systems that are made of pieces that perfectly fit next to one another. In such systems, they do exactly what we tell them to do, and consequently, the adjacency map tells us everything there is to know about the system. If I'm telling you who's sitting next to whom, you know what the shape looks like. Now, forget these Lego pieces in your dashboard in August in the sun and have them do this. By the way, I tried in August in Rehovot, didn't work. I had to put this in the oven, terrible smell. If you do this though, and then you try to make a Lego structure, the pieces don't fit next to one another, but if you force them to.
inverse problem, is it regarded like a solved problem, or what could one that want to design some morphing structure for a given material? What can you hope to what kind of assistance you can get from physicists when it is solvable, when it is not clear, it's still an open question, challenge?
So I think that the answer to that is threefold. First, even the forward problem is not fully resolved in all cases. But there are many cases where we know what the system attempts to do, but figuring out what is the bending minimizing isometry is such a non-local question that figuring out what the shape will do is a very daunting task. So even the forward problem in many cases is very difficult. Now the inverse problem, we have solved a variety of subset of questions. And everything that falls within those subsets can be considered resolved. In the sense that you give me a shape, I can give you the limitations or what approaches you can employ to get to the final answer. But there are entirely unexplored realms there and things that we have yet to understand.
Questions, everybody? This is the time for questions.
מיקרופון, בבקשה.
Also about the inverse problem and all that, do you need like specific materials to create those stress, or you can use like any material if you achieve to create that specific stress?
It turns out that there are several different materials that will all behave in the same fashion, that when I actuate them, they will expand by a certain amount in direction A and compact in the opposite direction. And those directions could change in space. One system is that of pneumatic elastomers, so these are liquid crystals that are frozen inside of polymeric mesh. You make them with pneumatic texture with a relative ordered phase, and when you heat them up, they go isotropic, and that's where you get it. But if you embed small air channels in an otherwise solid rubber tissue, and make all those channels connected to one another, then when you inflate them, they barely elongate along the length, but they go out of plane in a perpendicular direction, and consequently they shrink. And it gives you the exact same sets of equations. You can follow a different protocol by looking at shear-aligned, fiber-laden polymeric materials. So there are different strategies that all give you the same sort of physical behavior that gives rise to the same mathematical description.
Thank you.